I'm Jordan Becnel, and I'll be talking about the gas turbine experiment we're doing next week. First, I'll give a brief overview of what we're doing, what I'll be talking about. First, I have an introduction to the gas turbines, then I have the objectives of the experiment and some theory about it. Then I'll go over the apparatus and the procedure for the experiment, and then do some calculations and get some results. The jet engine is a gas turbine that is only used to produce thrust. It has an excellent weight to thrust ratio, so that's why it's very useful for airplanes. And it does have other uses, like this guy decided to strap it to the back of a Volkswagen Beetle and turn it into a jet powered car. The efficiency of a jet engine increases as the pressure ratio increases. And pressure ratios of jets have been steadily increasing over the past 40 years because of improvements in materials and the designs of the engines. And another way to measure performance is the specific thrust, which is the ratio of output thrust to the max flow rate of air through the engine. And you can increase this by increasing the temperature of the gas going into the turbine. So higher pressure and higher temperature gas entering the turbine results in a higher performance of the engine. These are the objectives for this experiment. First one is to understand the operating principles of gas turbine engines. Second is to record appropriate temperatures, pressures, and thrusts over a range of RPM. Third is to perform a number of calculations to quantify the performance of various components of the turbine. The thermodynamic cycle for the gas turbine is the Brayton cycle, and this is the temperature entropy diagram for this cycle. The solid lines are the ideal cycle, and the dotted lines is the actual cycle. And the gas goes through isentropic compression in the compressor, and then it has isobaric combustion in the combustor, and then it goes through isentropic expansion in the turbine, and then it's expelled into the air from the nozzle. This is the apparatus for our experiment. The gas enters over there and goes through the compressor, and then it goes into the combustor where it's combined with fuel and ignited, and then these combustion products then pass through the turbine and are expanded, and the exhaust from there goes out of the conversion nozzle and at a pretty high speed. This is the procedure for the experiment. The operating procedure is posted on the wall above the gas turbine. You do not operate it without having a technician there, and make sure you wear your eye and ear protection because it gets pretty loud. Then we record the initial load cell reading after starting it up, and then record pressure, temperature, fuel, mass flow rate, and thrust data at 10 different RPM settings. We were given some factory data to plot the fuel calibration curves, and what we had to plot was messed up, but it was fuel flow versus engine RPM and fuel flow versus the fuel meter. And what I did was I used a linear curve fit because I felt that it fit the data well and that it would be able to show how well the data fit. And I found that the engine RPM fit the data better than the fuel meter, so I think that would be the better, it would be the better thing to use to calibrate the fuel flow. And then we had to use three different ways to calculate the exhaust velocity. First way was using the air mass flow rate. The second way was the stagnation gas pressure at the exhaust. And the third way was using measured thrust. And I used a lot of different equations, but these are the main three that we used. And this is my plot for that. It's plotted against RPM, and the data for this was in a Google Docs that was posted on Google. And as you can see, that as the engine RPM increased, the exhaust velocity increased, which is expected because as the engine, works harder, you'll get more velocity, air velocity coming out. And also all three of the different methods came out with similar velocities, which was also expected. Any questions? It's fine if you don't have any questions.
Barbie? I don't know, here's a question.
So what can you do to increase the turbine efficiency? I mean, not the turbine, the efficiency of these?
You increase the air temperature and pressure that's coming through the turbine, like right before it gets to the turbine. You want really high temperature and pressure. But you don't want to increase, you don't want to do too much because you can run into like material problems, or even if you like put really good materials, it can get a really high cost trying to do that.
Why do you have a nozzle there? What's the function of the nozzle? Not sure.
To increase the speed press? Increase.
Right. It's just meant for increasing the velocity. Where do you use this? See the applications. Where do you use the jet engine?
Airplanes.
Right. And what do you need to have? Where is the nozzle? You need to have a lot of velocity, right? You need to have a supersonic velocity if possible. If not, then high subsonic. And the other question is, like, you see the configuration over there. You have a compressor, and then after the compressor, you have a combustor, right? So in the airplane engines, you will see that they have combustor cans. So they just don't have one combustor, but they have several cans over there. Those are the combustor cans. And the function of the combustor, like you mentioned, was just to increase the temperature, right? It's isobaric, but you're providing a lot of energy so that you increase the entropy. And right after the combustor, you have the turbine, and then you have the nozzle. So my question is, do you really require a turbine there, or you could have just done with the nozzle?
I guess it depends what you need it for. I think, well, you probably do need a turbine to expand the gas more.
Right. If you go back to your Brayton cycle, the cycle that you showed, you can answer from there. Why do you have a turbine? What's the function of the turbine?
It's to decrease the pressure and temperature.
You're having
When you have a really low pressure at the nozzle?
a low pressure at the nozzle?
Yeah.
You have high velocity at the nozzle.
So you have to have a low pressure.
So pressure is comparatively lower. Yes.
Yeah.
But if you have, let's say if you do not have a turbine, then you do not have any expansion. Like the function of the turbine is for the expansion of the gas, right?
Yeah, to make a low pressure.
Right. If you do not do that, you have all the high pressure gas straight away going into the nozzle. That might damage the nozzle, right?
Right.
So that's not good for the nozzle. You had a
The
question?
main purpose of the turbine is to run the compression.
Say that again?
Isn't the main purpose of the turbine just to run the compressor and compress it? Because they get
Yeah,
all
pretty much, yes. But then you are doing an expansion. The turbine is required for the expansion, right? Expansion of gas. So if you have to expand, without expanding the gas, you still have the high pressure. And then the high pressure goes directly into the nozzle.
I thought the expansion made the gas cooler.
Expansion would make the gas cooler. That's right.
Wouldn't it?
But not to that extent.
Okay, so it's just relative?
Yeah. I
Maybe
mean,
it can still be really freaking hot.
yeah, I mean, of course.
Yeah.
Of course, yeah.
Very good.
All right, any other questions? Yeah, Travis?
Do you actually take measurements for field pressure?
What's that?
Do you actually take data for field pressure?
I don't think so.
I'm just curious.
I think you can measure field pressure as well. That's just to check how much fuel you have. Like if it is a rich mixture or a lean mixture. If it's a lean mixture, you are very less air, you have more fuel. But then you can have incomplete combustion there.
And I was also thinking that high pressure can
Yeah.
also, increase ionization, so
Yeah.
it also increase efficiency.
All right, any other questions?